All right, deja vu. I want to revisit the BGA2869. I got a lot of comments on that video, mostly because of a stupid overlook I did. So is IMSAI guy going senile, or is there something maybe we can all learn from it? Well, first of all, if you do 2,000 videos and you spend about 10 minutes shooting off the cuff, yeah, you're going to make mistakes. So I'm okay with making mistakes because I think it helps people who are entering the hobby. They don't have to be perfect. If you watch YouTubes that everything is working every single time and you never see any blemishes, I think it actually hinders people from getting into the hobby. So don't worry about making mistakes. You'll make mistakes. So of course there's a 220 ohm resistor in here, and of course it's going to drop voltage. And I hadn't considered that it would drop that much voltage. And one of the reasons I didn't even, my brain didn't even lock onto that is because something I would never do as a designer. I would never, ever, ever use a single resistor to drop the voltage onto a part that requires a fixed voltage. So it didn't, my brain wasn't even registering the idea. Now people say, oh no, wait a minute. That's just the way mimics work, okay? And you're probably used to something like the MAR1 mimic that I talked about before, and it's just a simple, it's just a simple Darlington, and you have to have a resistor in order to make this thing work. It must have a resistor. And in fact, there's a table in them that, where's the table? Here. There's a table that tells you which value resistor to use for whatever voltage you're using. And you can't use a range of voltages either. It has to be a fixed voltage because you have to put in a certain current into these things to bias them correctly and stuff. So that's the way some mimics work. And so a lot of people would say, well, of course there was a resistor there because that's just the way it is. Well, that's not really true on all mimics, I should say. So this schematic or data sheet does not have a schematic. It does not show a equivalent circuit of what's inside this thing, okay? So I looked around just kind of for an example. So here's a real old part back when Hewlett-Packard was making mimics. So this is a 1 gigahertz mimic, okay? And here's its simplified schematic, okay? And it's a lot more complicated than just a Darlington, right? And it has a VCC pin, and this is a fixed 5-volt part. So it's similar. It's going to be similar to this BGA part. It requires a fixed voltage, no resistor. It assumes you have a low impedance VCC, and it has self-biasing networks. It relies on voltage dividers to set currents and stuff. So it's fabricated to be what it is, and I was assuming that's the same thing on this part, is that putting a resistor in the VCC line is just something I wouldn't have ever considered anybody doing. So anyway, not that I'm not an idiot sometimes. Yes, I'm an idiot oftentimes, but it's just why my brain didn't even pick up on it. So you can see this one has a fixed 5 volts here, and then it has some resistors on the plus and the minuses. It's got a push-pull thing on the output, and then feedback to the input, and so it's made to work at 5 volts. All right, so I thought what I'd do is, well, first of all, was this thing being biased correctly? Like I said, I believe it's this part, and this part is designed to operate between 4.5 and 5.5 volts. If you do the measurement, at 9 volts input here, you get 4.3 onto the part, and at 12 volts input, you got 5.8 volts onto the part. So the absolute max, I think, of this was, what, 6 or 7 volts? But you don't want to be operating it there. All of the specifications are done at 4.5, 5, and 5.5. So that's the way you're supposed to operate it. So even at 12 volts, this thing's operating 0.3 volts out of spec, really. And at 9 volts, it's out of spec also. It's 4.3 volts. So yeah, that single dropping resistor is not really going to make it correct If I was going to design this board, I would put a 5-volt regulator on the board, or maybe a Zener, but these days, just put in a 5-volt regulator, so you would drop the 12 volts coming in and have a 5-volt regulator to actually operate the part. So that's the way I would have designed it. But now that I believe this part is what I think it is, I'm going to make some modifications. I'm going to put a 0 ohm resistor where that 220 ohms is and make it into a real part. Now, something that people didn't mention is, well, what about the capacitor values that he used? And I talked about the really odd circuit layout that had an inductor and a capacitor, and you picked the location. Where was that? My fingers are dry. I was out walking the dog. This thing. Obviously, this board has nothing to do with that board. So there's no inductor, there's no fancy capacitor locations, there's no stubs and everything. Thanks for people who commented on the stubs. So if you take a look at this board, it doesn't match the datasheet either. The datasheet basically says you must use a 470 picofarad capacitor. That's basically how this whole thing was designed. So the bypass capacitor is 470 puff, and the 2 input and outputs were 470 puff. Now, there is a word of warning in here that says if you're going to be operating above a certain frequency, I think it was 100 megahertz, if you're going to be operating above 100 megahertz, you cannot use a capacitor larger than 470 puff. Well, what do you think the values of this board are? These are 0.1 microfarads. 0.1 microfarad, 0.1 microfarad, 0.1, 0.1. They're all 0.1 microfarads. So you've got these two in parallel coming in. So you've got this big giant 0.2 microfarads on the input. Anyway, it doesn't match what you should do according to, the people who designed the part, NXP. These are pretty smart guys. They're going to tell you how to use their part correctly. And so I think what I'll do is I'll put a 0 ohm resistor in there, and I'll replace all of these. I'll remove these 2 and replace it with just one 470 picofarad, and we'll put 470 picofarads here, and we'll see if it operates any differently and if we like it better. Well, I did do another thing, is I verified that it's a 50 ohm system. It is a coplanar with bottom ground plane, and I measured the widths of the traces and stuff. It's a 1.5 millimeter trace and a 2 millimeter gap side to side. So, and a 1.5 millimeter thick board as measured with my toolmaker microscope. And yeah, it all worked out to about 47 ohms. So definitely absolutely close enough. So that was a good design, but again, no inductor trace on the input. So I don't know how much that would affect things, but I think it would. And these 0.1 microfarad capacitors don't do a lot up in high frequency land. So yeah, let's make some of those changes and try it again. All right, we have it back on the VNA, and look, it's 30. Let's put a marker on it. It's 31 dBm, or dB, not dBm. 31 dB of gain, straight across, flat, up to 1.3 gigahertz. Perfect. Exactly how it should be per data sheet. It's working absolutely perfectly. And now, if we go to we go to reflection, and we look at the Smith chart, it looks really nice. So anyway, I say, if you put the right parts in and you design it correctly, that's a good part.